So the question is, from the scattergram, how do you get a production possibility? As it happens, the red line encloses or encompasses 98% of the ground animal or boreal animal data point. So it's a level curve. There's a joint density function over ground animals and arboreal animals. So what I did was empirically fit the joint density over ground and tree animals and then figure out the level curve on the density function.
This is done using the kernel method?
Yeah. Right. So I estimated my empirical density function as a kernel density. So I know I can create a data set that has all the points that lie on the red line. And my assertion is that that's a production possibility. It shows the trade-off in ground and tree animals. So why didn't I draw it so that it encloses all the data points? The reason is that hunting is inherently a stochastic process. And some days they're going to get lucky out of all proportions of their skill. And so they're going to be able to bring in a harvest that exceeds what they're technically capable of doing. They're not going to, there's no way in the world they could go out in the forest and come home with 225 kilograms of ground animals and nearly 200 kilograms of monkeys day after day after day. That day they just got really lucky. Apart from being really lucky, what happens is that it's a long hike from the rainforest back into the capital city. Or from the rainforest even out to the road where they hail down a taxi, they put their burlap bag full of their kill, their harvest, in a taxi, and it gets shipped into the city in a taxi. So sometimes they accumulate their harvest over several days, and then it turns up in the market. So there will be some days that lie outside this 98 percentile. The inner red line represents the sustainable harvest. The outer red line is what they're able to do. Given their technology and their skills, they're able to get the points inside the line labeled number 1. But, unfortunately, they're overhunting the tree animals and the ground animals. So the populations are collapsing. And as the populations diminish below a certain point, they collapse completely, and the monkeys and the ground animals are gone. But there ought to be a sustainable production possibility frontier. So the question is, where is that? So one of the things that we know is we know the morbidity and mortality rates of the monkeys and the ground animals. We know the carrying capacity of the land, and so on and so forth. So we can draw a sustainable frontier, which is labeled 2. So if they hunt within the frontier labeled 2, they could do that forever without collapsing the populations of the monkeys and the ground animals. Okay, so the way that we got the curve labeled 1 and 2 was to enclose a certain percentage of the points in a concave function, because there is a little wrinkle here, of course. This part of the curve violates the definition of productive possibility frontier because it's positive first derivative in the beginning there. And the first derivative has to be negative all the way. But there are some institutional reasons for why it turns down like that at the top, as well as some statistical reasons. But the important part of the way I got the curve is not through regression analysis, parametric analysis. I could have estimated a stochastic frontier, which basically is coming up with a parametric representation of the curve, and then sticking on the end a disturbance term that instead of being symmetric distribution like a normal distribution, is asymmetric. It could be, I could use a chi-square and switch the sign on this chi-square random variable. So that here's my parametric curve, and the probability distribution over the disturbance attached to the parametric curve can only take negative values so that I get stuck inside the curve. This idea behind stochastic frontiers, or envelopes, first came up in the estimation of cost curves. For example, suppose that's the true cost curve. Until, in economics certainly, until probably, well, there's a guy in the profession named Ron Gallant who's really been into nonlinear regression analysis for decades. But he's kind of a little cottage industry all for itself. really smart guy, but never really caught on. It was very hard to understand the statistics of nonlinear models. But the mathematicians and the statisticians have been thinking about nonlinear or non-parametric estimation for quite a few years, and kind of made its way into the economics profession. So the economics profession first stab at things was to say that if this is the true cost curve, all of our data points really have to lie above the cost curve. All the rules about firm behavior tell us that you can never produce a given Q for less than the cost corresponding to a point on the curve. But inefficient firms will lie above the curve. No problem. So our problem as economists is to figure out a way to fit a curve that in a statistical sense supported all the quantity cost pairs. So I could have done that. I could have used that kind of stochastic parametric frontier approach here. And I did try it. It didn't work out too well. And I'll explain that why in a minute. But that was Gallant's approach, and the approach of a few others who have worked with him on the stochastic frontiers is basically parametric. And they're still applying the principle of least squares. They're measuring their error as the difference between what they observed and what they predicted. So this is the y that they got, and that's the y that they predicted, and the error that they made, they measure in the vertical dimension. You could invert the data, and you could measure the error going horizontally, but you don't really gain anything by doing that. Yeah. Oh, I'm sorry. What's a y and a c between friends? There you go. So how does this approach, this least squares approach, which is inherently parametric, differ from what I did? In this least squares parametric approach, my predicted C is a weighted average of all the observations on C, where the weights are constructed out of all the Q's. Just like when I had a scattergram that looked like that, and I had X, and I had Y, and I fit a line through the data, and I had Y, I had a given Y, and I had a Y hat. My Y hat is a weighted average of all the Y's that I observed, and the weights are constructed from all the X's that I have in my data set. Over here, in effect, what I did with kernel estimation was I said, let's take a rectangle in the GA plane and compute the frequency, compute the average frequency over the GA pairs in that rectangle. And that gives me, and I have the midpoint in the rectangle, and I computed the frequency of all the GA pairs that fell in that rectangle. And that's a point on my level curve. And then I said, let's move the rectangle a little bit and compute a new frequency of all the GA pairs that fell inside that rectangle. And that's another point on my level curve. And then I moved it, so you can see that, for example, these two data points, they are members of both rectangles. But these data points, while they were a member of the lower rectangle, are not a member of the older one. So I'm always changing the data points that get included in the weighted averages that I'm constructing. So that's an important distinction between what's going on over here and what we've been talking about all semester here, where my Y hat is a weighted average of all the Y's, where the weights are constructed from all the X's. Over here, I have a predicted frequency, which is based on only some of the G's and some of the A's, not all of them. By changing the dimensions of the little box that I'm working with, I could include more data in the computation of frequencies. So that's an example where you could use that stuff.